We'll create a PLL with analog rails. This is a phase detector. All logic cells are built into analog rails. They initially arrange in the same relative order as the schematic. They snap together like Lego blocks. We also have an automatic alignment tool. Let's arrange the blocks of digital. Then we're going to add a bounding box and then route it. Isn't that automatic routing nice? We're going to now create an amplifier. This amplifier we're going to use in the charge pump. We're going to create it from scratch. The schematic is very similar to Virtuoso. We try to use the same bind keys. We could read from Virtuoso, and the output, it goes back into the same database, open access, as Virtuoso. So you could open it up in Cadence. It's plug and play. Yeah, the pins, we automatically generate the symbol. The pins get automatically added to the symbol. We're going to put the compensation, RC compensation, on the outside of the block. Let's simulate the amplifier. We'll add the analysis components, transient, AC, op point. We also add measurement components. We have settling time, overshoot, gain margin, phase margin, all that stuff. We're going to set the variables, and we'll also set up the corners, typical, fast, and slow. We're simulating with Zeiss. We supply an infinite supply of that simulator. And as you could tell, the simulation results isn't completely perfect, and we're probably going to want to optimize it. So you can see all the measurements, and now we're going to start optimizing that amplifier. We're going to be matching the differential pairs and the mirrors. And what that does is it locks the widths and the lengths of the match devices so they move together when you optimize it. During the optimization run, we show the schematic seed. And then as the optimizer runs, the user can run local optimization or global optimization. And you can run on multiple computers in parallel to speed up the results. When the result hits green, that means you've hit the spec. When we hit the spec, what we're going to do is we're going to apply the results of the optimization, and then we're going to move towards creating the final layout. Okay, now we're going to run the layout of the amplifier for the charge pump. We have automatic layout matching. We're going to match devices. Differential pairs matched. Current mirrors. We have common centroid. User could change the number of rows, number of dummies, different configurations. We have a robust library of different choices for differential structures. If you have even number of rows, it will be common centroid. After we place all the structures, we're going to automatically route it. When we do add the power supply is differentially route aware, so the power supply mesh will never cause a conflict or mismatch of the differential routes nor the differential structures. Okay, now what we want to do is we want to finish this charge pump with our newly optimized amplifier. To instantiate the amplifier, hook it up in the schematic. We're also going to flatten or smash the layout. When we do that, you'll notice that we never lose cross probing between the schematic and the layout, even though that block is flattened or what we call smashed. Same thing. And we situate it within the charge pump, and then we're going to add the horizontal power supply trunks, and then we will automatically route it. And you'll notice once again that we never cause mismatch in the differential pairs nor differential routes. Isn't automation nice? Now we have a test bench. We're going to simulate the combination charge pump and phase detector. And what we're going to be doing is we're going to try to make sure that when the both input signals arrive at the same time, we want the integral of the current of the output high versus output low to be the same. We have different phases coming in. The first few stages, first few pulses, the high input is faster, then they arrive at the same time, and then the down input comes in faster. Okay, now we're going to run the counter synthesis. So here we're going to synthesize an up-down counter. The synthesis tool, after creating the gate level netlist, will then automatically generate a schematic from that using our AR logic standard cells. And then we place and route. The user could change the number of rows, the size of the PMOS, NMOS. All our AR logic is parameterized. We place it, route it, run timing, and then you run feedback loops to hit the timing that you need. VCO. There are 4 differential stages chasing each other around in a circle. We will butterfly match them with cloning. Let's make a layout of the master group. Let's get the other components out of the way. This is the V to I converter. Doesn't really need to be matched. Now let's go back to cloning. We put a group box around the master. We're going to set the number of rows for your final arrangement. We will use the letters P, Q, B, D for the relative orientation. The master will be automatically routed. Then the editor will prompt the user to input each slave device that is matched to the master. Once the primitives of the 3 slave stages are done, the layout will be created as per the requested sets of rows and orientation. And then we're going to route the whole thing. Now we're going to run the parasitic extraction. Notice that the capacitive values back annotate into the schematic on the wires. Now we're going to do the top level of the PLL. We're about to finish the job. The placement was already created, and all that's left to do is add the power mesh, the trunks of the VDD, VSS, DVDD, DVSS, because we have dueling power supplies, meshes at the top level, and then we're going to route the whole thing automatically, finishing the PLL.